In this lesson, we will learn some things about capacitance. It is not all-inclusive of everything we need to know on this topic. Additional information can be found in the General Aviation Maintenance Technician Handbook and in Acceptable Methods, Techniques, and Practices of Aircraft Inspection and Repair. A capacitor consists of two conductors separated by a dielectric material. Dielectric material is a good insulator and capable of passing electrical current, but is capable of passing electrical fields of force. Oftentimes the conducting plates are thin sheets of metal foil separated by a special paper serving as the dielectric. The foil and paper are then rolled up together, creating a capacitor with large conducting plates in a relatively small size. Once charged, the capacitor will have an excess of electrons on one of the conducting plates and positive ions on the other. The unit of measure of capacitance is the farad. In a circuit containing a capacitor, the voltage source or battery will drive electrons from its negative terminal to a conducting plate of the capacitor. As electrons build up on that plate, they will repel like charges, meaning other electrons, from the opposite plate, leaving it with a positive charge. There are three factors affecting capacitance. The capacitance increases as the size of the conducting plates increase. The capacitance increases as the dielectric constant increases. And the capacitance increases as the distance between the plates decreases. The dielectric constant is a numerical rating of a dielectric material's ability to hold a charge. On the right here you can see a chart of some common dielectric constants. Air is the reference dielectric and is assigned a value of 1. There is no need to copy or memorize this chart. It is only put here as a reference. At the bottom of this slide is a simple schematic containing a battery, a capacitor, and a double-pole single-throw switch. This schematic shows electrons flowing from the negative terminal of the battery and collecting on one of the plates of the capacitor, and electrons being driven from the opposing plate into the positive terminal of the battery. This process will continue until the potential difference across the capacitor equals the potential difference of the battery. Once the capacitor is charged and the switch is flipped, electrons will flow from the negative side of this capacitor to the positive side until the capacitor is discharged. Capacitors may be connected in a circuit just like resistors. Capacitors in parallel are added together like resistors in series, and capacitors in series are added together like resistors in parallel. Here we have a simple schematic with three capacitors in series. The symbol mu means micro, or 1 times 10 to the negative 6. Therefore, 8 mu farads equals 8 times 10 to the negative 6 farads. Remember, capacitors in series sum like resistances in parallel. The total capacitance of this circuit is therefore 4.32 mu farads, or 4.32 times 10 to the negative 6 farads. In this example, we have three capacitors in a circuit parallel to each other. Remember, capacitors in parallel add like resistors in series. In a capacitive circuit, changes in current lead changes in voltage. When power is added to a capacitive circuit, current begins to flow immediately. However, voltage only begins to increase as the plates become charged. The time constant is the time required for the voltage across the capacitor to reach 63.2% of the remaining difference between it and the source voltage. The time constant, tau, of a series RC circuit is the product of the resistance and the capacitance, where tau equals the time constant in seconds, R is the resistance in ohms, and C is the capacitance in farads. Capacitors charge fairly rapidly, but they do not charge instantly, nor do they charge linearly. During each time constant, the capacitor charges 63.2% of the remaining distance to the maximum voltage level. A capacitor is considered fully charged at the end of 5 time constants. Capacitors discharge at the same rate they charge. Reactance is the opposition to current flow presented by capacitors and inductors. Capacitive reactance is equal to 1 over 2 times pi times the frequency times the capacitance. If capacitance is held constant, what happens to capacitive reactance if frequency increases? As the frequency increases, the capacitive reactance decreases. What happens to resistance across resistor as frequency increases? Nothing. The resistance does not change. Remember that the capacitance of a capacitor is dependent upon the dielectric constant of the dielectric. Fuel and air both act as dielectrics with different dielectric constants. As the fuel-air ratio changes, the average dielectric constant of the mixture changes, affecting the capacitance of the capacitor. The fuel quantity indicating gauge reflects those changes in capacitance.